So you will have a macroscopic number of atoms in the ground state. You will have a macroscopic number of atoms all with the same wave function, what is called a giant matter wave. But at the time of Einstein, when you calculate the temperature of the condensation, you find microkelvin, nanokelvin. And at that time, that was not available. And the calculation of Einstein was done for a perfect gas without interaction. And at this temperature, all substances are in solid state or in liquid state. The thermodynamic equilibrium in solid or liquid. So describing a solid or liquid by a perfect gas is rather difficult to admit. So the prediction of Einstein was welcomed with a certain skepticism, even himself. He was not believing. He said that purely academic consideration. Of course, when superfluidity was discovered in helium, London suspected that it had something to do with Bose-Einstein condensation. But you know, liquid helium, you cannot ignore the interaction because it's a liquid state. So the question was not clearly solved. But now with laser cooling technique and with evaporative cooling, you can reach easily temperature less than 1 microkelvin, and you can reach the condensation threshold for a gas where interactions are weak, because you have only two-body collision, and you can observe it. And that was observed in '95 by Eric Cornell, Wolfgang Ketterle, and Karl Reimann, and they got a Nobel Prize in 2001 for this important discovery. And what I would like to let me switch rapidly to the last part. Why they are important? Because these condensates, these giant matter waves, have macroscopic quantum properties. You can observe them by eye. A condensate, you can observe a condensate by eye. It's a few hundred microns. With a microscope, you can easily observe it. There are macroscopic properties like superfluidity, coherence, which are very similar to properties which up to now were observed only in dense systems like superfluid helium or superconductors. Okay? But now you observe them on dilate systems about 100,000 times more dilate than air. And in this system, interactions are much weaker than in a solid or a liquid, and you can include interaction in the theory. And you can predict what will be the effect of interaction. And furthermore, by using a phenomenon which is called Feshbach resonance, you can change the collisional properties of two atoms by tuning a magnetic field and make the gas, the whole gas, either with effective interaction which are attractive or repulsive or zero. You have a knob allowing you to change the sign of the interaction between atoms. So you can vary all parameters, the temperature, the interaction, the field, and you can have a much better understanding of what happened. And this explains why there are a tremendous number of papers, about 1,000 papers appearing every year on Bose-Einstein condensation. Really a lot of new theoretical and experimental studies have been stimulated for this experiment. And perhaps before concluding that I have just 2 slides now, let me just list a few possible applications of the manipulation of atoms, which I've tried to explain to you. There are a lot. You can make magnetometers or measures with optically pumped atoms. You can make MRI of the lung with optically pumped helium-3 atoms, which I've described to you. You can make atomic clocks with accuracy reaching a few 10 to minus 16. You can make atom lithography, because by using atom optics, you can focus an atomic beam, a slow atomic beam, with a nanometer precision on a substrate. And you can deposit atoms on a very narrow substrate. You can make nanolithography. You can make atomic gyrometers, gradiometers with de Broglie waves. You can make what is called atom lasers. Let me explain to you briefly what it is. You know, an optical laser, it's a cavity, 2 mirrors, and in this cavity you have a set of modes. a mode is some sort of a quantum state in the cavity. And one of these modes contains a macroscopic number of photons, some sort of Bose-Einstein condensation of photons. Okay? And one of the mirrors is not perfect, and you have a beam of coherent photons going out of the cavity. Now, it can do the same thing with atoms. You have in a trap a set of energy levels. One of these states is macroscopically occupied by a million atoms, okay? And if you make a small hole in the trap, you extract from the trap a coherent beam of de Broglie waves, which is now called an atom laser. It's equivalent of a laser, except you replace electromagnetic waves by de Broglie waves. And that's an example of atom laser. This is a condensate and the coherent beam of atoms, very parallel beam going out. And we expect to have a revolutionary application of this scheme for atom optics, for atomic interferometry. Another scheme which is extremely important, which I have no time to explain, but it also a lot of new laboratories are starting this type of research, is that our ability to manipulate atoms now allows you to prepare what is called qubits, quantum bits. You know, in classical information, is based, classical computer like this one, are based on bits. Bit is bit information, plus or minus, 1 or 0, any two-state system. But in classical bit, you have either 0 or 1, or plus or minus. In quantum mechanics, you have also two-state system, spin up, spin down, or G, E. But contrarily to classical mechanics, now when you have a two-state system, E and G, you have not only the state E, not only the state G, but you have all possible linear superposition of E and G. You can have C1E plus C2G, where C1 and C2 are two complex numbers. So a quantum bit can exhibit a number of possible states, usually more varied than a classical bit. These are called qubits. And people are using this qubit now for information, for making, for example, cryptography. Now it works very easily. You have what is called now quantum cryptography, which allows two people to communicate with correlated photons, being sure that no spy can detect what they exchange. And of course, there are a lot of possible thinking about achieving a multi-register system using qubit and achieving a quantum computer. I'm not sure that this will soon achieve because there are a lot of difficulties, but of course, if a quantum computer is achieved, I don't know, in 2 or 3 or 4 decades, that will be a dramatic improvement over classical computers. So there are a lot of hopes about that. And once more, I would like to emphasize that all these applications, which I described here, were not planned in advance. They were the result of basic progress in basic research. And I think that when you take the history of science, you see that in technology, all the technological improvements are discontinuous. I'm sure that a few of you have still vinyl records, micro-sillon, you know, the vinyl music for music player, you know, 33 turns per second or 45. That was 20 years ago. And then the CD came with laser diodes, and that it becomes completely obsolete, the vinyl record. And now the MP3 music makes the CD even obsolete. And I think that every change in the technology is discontinuous. So if you try to improve a given technology, and if you neglect basic research, you can be completely out within 10 years or 20 years. And I'm sure that the technology we will use in 20 years from now will be the result of what is done in basic research in laboratories now. So we have to be careful to keep basic research active and not to give only applied programs for solving this problem, this problem, this problem. We have to keep a very active basic research. That's my profound feeling. And so my conclusion is that our ability to control, I hope to have convinced you that our ability to control and to manipulate quantum systems have considerably increased in the last few decades. We're now able to detect atoms one by one electron, you can even detect a single electron and observe it for a long time. You can detect a single molecule, a single ion. You can detect the light emitted by a single atom. And that is opening completely new research fields, which were completely impossible to imagine a few years ago, allows us to ask new questions. And when we ask new questions, in fact, it's always extremely important because we are expected to make new discovery and to discover new states of matter like condensate. And I think also that one can reasonably expect that this will lead us to a better understanding of the basic physical law, to a better understanding of the world which surrounds us, and also certainly to interesting new applications. And in my opinion, it's important to support basic research. First, because it changes our vision of the world. Every new discovery changes our vision of the world. I think it's important for solving the various problems we have to face. We have to find new source of energy. We have to improve our environment. We have to improve our health. I think this will be achieved by doing more science, not less science. There's some sort, unfortunately, general attitude now which is developing, considering science as bad, producing more inconvenience than advantages. I think that's a big mistake, that we have to do more science if we want to solve our problem. And I think also we have to improve the scientific education, because scientists learn to be modest, learn to have a critical mind, to ask questions, to change his mind if it is necessary to change his mind. And I think that is very important because that can allow us to fight against intolerance, fanaticism, racism, which unfortunately is plaguing the beginning of the century. And in fact, in this way, for promoting the establishment of peace between nations, which is one of the programs of the Foundation for Peace, which is supporting this series of lectures. And thank you for your attention.
Now we are open for questions from the floor. Please.
Thank you for your presentation. It's very nice. I'm not a physicist. I am a computer man. So maybe my question is,
you are?
I'm an IT person.
Yes.
Okay. Sorry if my English is not very well. My first question: when the atoms are cooled down, how can you preserve the energy level of atom?
Excuse me, I didn't catch your question. How did you start this research? Or?
You cool down the atom.
Yes.
And you have to preserve that level of energy. When atom cool down, it will receive energy from outside environment. So how can you preserve that energy level?
I've shown you freeze them by letting them interact with a set of laser beam with frequency which are appropriately chosen and direction also correctly chosen. And then you measure the temperature by the time of flight technique which I've described. And an experiment takes about 1 second for trapping atoms, for cooling them, and for detecting the temperature, for measuring the temperature.
So you continuously inject the laser to the atom?
Yes. You can introduce atoms and cool them as a function of time.
So this method, you just, actually electron receive the energy from photon and up to the excited state, yes, and then back to the ground state. How can this affects the atom velocity? The nucleus of atom are not impacted by photon, just the electron. But how can
You know, the atom absorbs a photon, goes to the excited state and falls in
Yes.
the same state, and then absorbs a second photon. This one movie which you presented, you can imagine that you are walking in the street and you have a heavy storm with hail, you know, hail grain. And when you walk, you have all these hail grain hitting you, and you are more and more difficulty to walk, and you are slowed down. It's exactly the same picture.
It hit electron, not
What?
hit the nucleus.
What?
The photon hit the electron.
The photon, the photon is absorbed by the atom, by the ensemble of atom and nucleus, electron and nucleus, and then it is re-emitted. You can consider that it bounces on the atom, absorbed and re-emitted. But you know, the absorption process, it goes from in a given state to an excited state and falls back. And you know, there is a difficulty if the atom does not fall in the same state as the state from which it started, then the process stops. You have to repeat the process a million times per second to have an efficient cooling, stopping effect. And that's what happens in molecules, because in molecules you have many, many levels, rotational, vibrational levels, and when a molecule absorbs a photon, it falls down not necessarily in the same vibrational state as the state from which it started, but in another state, and then the process stops. So it's very difficult to cool molecules by laser cooling. You see, because you have not a closed system. You must have a closed transition. You start from G, you go to E, and you have to fall in the same G to repeat the process a sufficient number of times. If you have many states in the lower state, then you can lose. Alors, many people have tried to different schemes for cooling molecules, and it turns out that the best way of cooling molecules is to start by cooling atoms and then to combine them to form molecules. And now people are able to form cold molecules and even to form condensates of molecules. The first condensate of molecules have been observed by 5 different groups a few months ago.
Okay, my last
People
question.
have been able to produce condensate of molecules.
Okay, my last question. Why did atom must spin? It's always spin, right? Why this it must spin?
The last step,
Atom spinning. The atom will always spin in natural. That's right.
I'm sorry, I did not understand the question.
Um,
Why? Why atoms have spin?
yes.
You know, 2 different reasons. First, you have orbital momentum. The electrons orbit around the nucleus like a planet around the sun. Orbital. And second, each electron has an intrinsic angular momentum which is called the electron spin. In very crude terms, you can see that each electron rotates itself, and it has an intrinsic angular momentum. And the angular momentum of the atom is the sum of all these angular momenta. So you have to go into the detail. But the atom as a whole has an angular momentum, which contains part of orbital angular momentum and part of the spin angular momentum. But to keep things simple, I've considered only the total angular momentum.
Is this property related to the spinning of object in the space?
Yes, sure. But you know, the spin of the electron is a property, it's a typically quantum property you cannot understand in purely classical terms. It was predicted actually by a relativistic quantum mechanical equation called the Dirac equation. And it was suspected by Uhlenbeck and Goudsmit to explain the atomic spectra. And Pauli introduced a non-relativistic description of the spin. But the interpretation of the spin, the correct interpretation, came only within the framework of relativistic quantum theory by Dirac.
Thank you very much.
But you have to admit, because I cannot introduce the whole quantum mechanics theory, you have to admit that any elementary particle has an intrinsic angular momentum which is called its spin.
Well,
Thank you.
I guess I have another question that related to what we are talking about here. So when we trap the atoms,
Yeah.
but the electrons inside is still spinning, is still moving. So I'm wondering, like, what is the effect of these electrons to how cold we could go? Like, what is the limit? How cold we could cool down the atoms? And what about the uncertainty principle? Does it have any effect on this
a very
at all?
interesting question. We know all from our quantum mechanics course that we have between delta x, spread of the wave function, and delta p, the spread of the momentum, delta x, delta p on the order of h bar, with h bar over 2. Okay. So to get absolute zero, you have to get delta p equals 0. But if you take delta p equals 0, because of the uncertainty relation, you have delta x infinite. So in principle, you cannot reach the absolute zero because then you would need to have an experiment in the whole universe. Okay? So you are limited by the size of your experiment. But let me give you an order of magnitude. If you have a few nanokelvin atoms, 1 nanokelvin, delta p corresponding to 1 nanokelvin, the corresponding delta x given by the uncertainty relation is about 30 micron. Okay? So the spread of the wave function is of the order of 30 micron. But 30 micron is still smaller compared to the size of the experiment. So we are not yet limited by the size of the experiment. Of course, if we go to much, much lower, at certain limit, we will need to enlarge our experiment, but that will occur only if we reach temperature of the order 10 minus 15 Kelvin, which is still far. But you are right. In reality, in principle, we can never reach delta p equals 0, t equals 0, because to reach delta p equals 0, we would need to have wave function extending over the whole universe, which is obviously impossible.
Thank you.
But with ordinary experiment, with an experiment of a few centimeters size, we are still some space to still cool down atoms.
I have more questions from the floor. How precise do you need to control the wavelength of the optical power of the laser in order to focus all these atoms and trap the atoms?
The accuracy with which you can determine distances?
Okay, like how precise do you need to control the wavelength and the optical power of the laser beams?
If I understand your question, see what is the accuracy with which you can determine distances with laser light? Oh, this is. Oh, that depends. That people have put corners in the moon, and they send the laser beam on this corner, which is reflected back, and they can determine the Earth to moon distance, I think, with an accuracy of a few millimeters. And in satellites, I think that with also by laser light going this way and back, they can measure the motion of the waves also of the ocean with a few millimeters accuracy. And they can measure, with laser light, you can really, with short pulse of light, you can determine distances with extremely high accuracy. And that's very important for understanding geophysics, for example. But that's a different field of application of lasers.
And another question from the floor. Could you please explain the light shift? Why does the detuned laser change energy level?
Excuse me, why the D2 laser?
Well, maybe the person who wrote the question could ask this too if I didn't ask that clearly. I think what he or she would like to know is about the light shift. I think you mentioned that a little bit in the beginning of the talk.
How can we measure the light shift? Is the question? Who has the question?
Could you kindly explain why there is a light shift? Why the detuned laser changes the energy level?
Yes, I can explain it. I would need a blackboard, but if you take, let me take a purely quantum description. Suppose that you have a two-level atom, And let me consider two states, atom in the lower state G, okay, with n photons, n infinite photons, Gn. And let me consider another state of the system, atom in E with one photon less, En minus 1. Okay? So you have two unperturbed states without coupling. If omega L is equal to omega A, the two states would be degenerate. Because by going from Gn to En minus 1, you increase the energy by omega A, and you decrease the energy of the field by omega L, and the distance between the two levels is just finished. You see, the two states are degenerate if the detuning is equal to 0. If the detuning is not equal to 0, you have the state Gn and the state En minus 1, which are separated by a splitting, which is the detuning. And when you introduce the coupling between the atom and the light, you have a two-level system with off-diagonal coupling, and the two levels repel each other, and that's the light shift. If you want a more classical explanation, the light beam induces a dipole moment on the atom, which oscillates at the frequency of the light beam. And this induced dipole interacts with the incoming light to give some sort of polarization energy. And people also sometimes call the light shift the AC Stark shift. You know, a Stark shift, I don't know if you know Stark shift, it was discovered by Stark. It showed that an atomic state in a DC electric field is shifted. That's called the Stark effect, which is equivalent of the Zeeman effect for electric field. If you replace the magnetic field by an electric field, you have a Stark shift. But if you have, and the Stark shift is quadratic in the electric field. But if you have an optical wave, it's a cosine electric field, and since it is quadratic, the shift due to Stark effect is proportional to E squared cosine squared omega t, and you have a DC part which produces a shift, a DC shift of the level. This is what is called AC Stark shift.
Please.
We have questions on the atom manipulations, and how did the IBM nanotechnologists can manipulate individual atoms without reaching Bose-Einstein condensation before the experiment.
You mean what kind of application in nanotechnology with cold atoms? I've mentioned one of them, which is using atom optics. You know, you can use laser beam to focus an atomic beam, and you can focus it to size which are of the order of the Broglie wavelength. And by using atomic beam, very coherent atomic beam, you can make focus the atomic beam with a distance on the few nanometers. And you can deposit atoms on lines or make some picture which are in the nanometer scale, 110 nanometer scale. Whereas when you do ordinary lithography, you use light, and the size of the structure you can make is limited by the wavelength of the light. This is why people go from optical to X-ray or UV to make narrower and narrower structure. With atom optics, you can go much farther down. The problem for industry is that the price of the photon is high. You have to produce in industrial way nanostructure by atomic lithography. It's more expensive than using optical masks. And this is why atomic lithography is not yet developed enough. But I'm sure that the progress of technology will occur and will make of this technique a very powerful technique. Also now, it's possible, something which is very interesting, it's possible to, by making standing wave with light beam, it's possible to make a 2D or 3D periodic structure of potential wells where you can trap atoms. that's called optical lattice. It looks like a box for eggs. You know, a box for eggs where you have eggs in each hole. You can do the same thing with potential waves which are produced by light, standing wave, and you can trap atoms in this way. And by using Bose-Einstein condensate, it's possible now to be sure that you have only one atom per site. And you can make a regular array of atoms with one atom per site. And you can control this array as you want. And of course, that is a very micro nanostructure which have a lot of application.
In IBM, they claim that they can do atom manipulation by using AFMs, the atomic force microscope.
Yes, sure,
right?
sure, of course.
So
of course,
it seems
another example of manipulation of atoms with force microscope. Yes. You can determine and move atoms one by one. That's a different approach, using a tip and using the van der Waals forces between the tip and the background. Yes. But here you use light.
So when AFM tip has been touched with the atoms,
yes,
the energy level is not disturbed.
Yes, sure.
Anyhow.
Sure. And there are people trying to combine atomic force microscopy with laser light. You can excite the molecule or the atom which is analyzed by the tip. And there are people trying to combine both techniques, the tip technique and the optical technique, to manipulate atoms in a more clever way.
And the last question from the floor.
Before I go on, thank you for the illuminating lecture. I'm intrigued by your last conclusion about fight against intolerance and fundamentalism by basic research. During the past few decades, we see an explosion of scientific knowledge due to basic research. At the same time, we see an explosion in violence due to fundamentalism and due to intolerance. Would you care to give an explanation to that? I believe the same thing, but I am disturbed.
You mean you want to understand why, in despite of this impressive progress, the people, less and less people are trying to do science in students, or no?
You see, people fighting one another. Look at Taliban.
Yes.
There are all these fundamentalism, violence going on in the world. At the same time, we have an explosion of scientific knowledge due to basic research. And in your last conclusion, you said, well, we should do basic research to fight intolerance.
You know, it's a question of politics, I think, because I think that most politicians don't know really what is basic research, and they don't consider long-term projects. You know, politicians usually have a short-term view, 4 years of view of what is going on. And you know, my experience is that to make a group working, the time scale is much longer, more 20 years. It takes 20 years for forming good people working together and reaching an international level and producing important results. So basic research is a long-term investment. And you know, most politicians want to have results during their mandate, which is 3, 4, 5 years. And they want to support programs with well-defined objectives. For example, they want to solve the cancer problem, or they want to solve, I don't know, the AIDS problem, or the energy problem, or the environment problem. So, of course, it's important to maintain a high level of development research. But you know, basic research takes a much longer time scale, because it tries to form good people, and that takes time. And you know, as I mentioned if you look at history of sciences, the time lag between the discovery, the basic discovery, and the application is more or less 20 years. Before a basic discovery becomes a very useful technology, it takes 20 years. And you have to keep alive a community of people working in basic research if you want to remain in the competition for technology, and also for a competition for basic knowledge and understanding better and better what is nature. That's the first point. And I think that, in my opinion, it will be important that the managers of companies, big companies, or the politicians, should receive formation by research during 1 or 2 years. They should spend 1 or 2 years in the lab, in the research lab, to know what is research. And that would improve dramatically the situation. And when I look at the big companies in the United States which were successful, like Hewlett-Packard, Apple, Spectra Physics, Coherent, all of them were created by young people having a PhD, having a good experience of research, and able to innovate, to make innovative discoveries, because they had an experience of what they do. Now, at least in France, what I know, most managers of companies have a, I would say, management experience. They have a management formation, and unfortunately, a lot of them prefer to invest money in stock exchange to make profits for the action, rather than investing money in long-term development. And I think that is a mistake. At least this is my point of view.
Thank you. And for any of us that have more questions, we'll be able to do that, have further discussion in the reception. So now I'm very intrigued of how you explain these advanced matters in such a simple way so that we can understand. Not only this lecture increase our knowledge of interactions between atoms and radiations, which is a result of increased control of the atomic motion. Also, the possible practical uses of new advances, as well as how important the basic research is. As an appreciation of you coming here, the director of NECTEC, Dr. Thurisak Gaur Anantragun, will present you a souvenir.
Oh. No. He can go back and forth. Oh, thank you so much. Thank you. Thank you so much. Thank you.
Science Park.
Ah, that's a picture of the institute. Thank you.
Information about me.
Thank you very much. Thank you.
I also would like to invite Dr. Manoon Aram Rat, the Inspector General from the Ministry of Science and Technology, to present a souvenir and address the closing remarks.
Oh. Thank you very much. Thank you very much. Thank you very much. It was his birthday.
Yeah, his birthday was 2 days ago.
Thank you very much. Appreciate it very much. Thank you very much for all these gifts.
Professor Cohen-Tannoudji, distinguished guests, ladies and gentlemen, it is a very privileged opportunity for us all today that we have the opportunity to listen to Professor Cohen-Tannoudji, the Nobel Laureate in Physics, about waves and atoms. He has presented to us the relationship between atoms and waves, which picks on our brain waves to follow the waves of atoms and matters. I'm very impressed and very appreciative of the simple way of the presentation of wave. Now in Thailand, we have just woken up about the nanotechnology about 6 months ago. After listening to your presentation today, we know what we excited about 6 months ago is becoming obsolete. Because not only you present us the possibility of many applications of light and atoms and different phenomena of new discoveries which can lead us to new frontier of nanotechnology, which we are struggling to understand. And perhaps in the future, before Thailand can master nanotechnology, perhaps in France, you have already mastered the atomic technology, which is smaller than nanotechnology. One example you explained is a possibility to have the atomic lithography, which is a very bring great hopes that in the future all the electronic appliances or gadgets will become even smaller, and microchip we talked about today will contain more cells of transistors in atomic level. And that kind of vision, that kind of development that we need to learn, we need to understand, even though we cannot readily follow it in laboratories, but to understand the level of discovery in the world is also important in itself for us, for our science community. On behalf of Ministry of Science and Technology and on behalf of our audience here, I would like to thank you, Professor Cohen-Tanoudji, for his kind presentation. And we are hoping that his presentation will inspire, will be good information and inspiring to our new scientists, our new young scientists, to follow suit, to keep up with their good research, and hopefully Thailand in one day we will also be able to conduct such advanced research in the future. I thank you, Dr. Cohen-Tanoudji, and also hoping that we will have opportunity to receive you again in the future in our laboratories. Perhaps our young scientists will have opportunity to become your students, to become your researcher, to research with you. Thank you very much.
Before proceeding to Chom Suan Room for the reception, I would like to ask Professor Claude Cohen-Tanoudji, Dr. Twisakon Nantakul, and Dr. Manun Aramrat for a group photograph. And later on, if any of us on the floor would like to have pictures, like good pictures, with Dr. Cohen-Tanoudji, we are welcome to. Thank you.